In this video, we're going to be talking about nucleophilic addition reaction of aldehydes and ketones. In our previous video, we started looking at aldehydes and ketones, how to name them, and if you haven't seen that video, you can check it out on our playlist. Alright, so in our introductory video, we did mention that the carbonyl group is a polar compound in the sense that we have two groups like this, R1 and R2, which is bonded to a carbon and doubly bonded to oxygen. And we did mention that this oxygen here is partially negative because it has lone pairs, and the carbon is partially positive, and this makes the carbon to be electrophilic, and in that sense it is going to be attracting nucleophiles. So it is quite sensible, and it's really sensible, of course, to say that carbonyls can undergo nucleophilic addition reaction. And we know that in aldehydes, either R1 or R2, let's call this R2, either R1 or R2 is a hydrogen. If it is a hydrogen, then we know that that is an aldehyde. But if both R1 and R2 are alkyl groups or aryl groups, then we know that it is a ketone. Alright, now one thing too we have to take note is that there is low electron density on the carbon, like I mentioned, and the oxygen over here has lone pairs on it. It has lone pairs, and so it can act as a Lewis base in the sense that it is a site for protonation. So we consider the oxygen over here. This oxygen acts as a Lewis base, and by that I mean it is a site for protonation. What it means is that anytime we have an acid in there, the oxygen donates one pair of electron to pick a hydrogen. Alright, so we can say that the carbonyl oxygen is nucleophilic, which means it will be attacked by an electrophile. Just like I'm saying, if we have H+, then it's going to pick it up. And now let's look at what actually happened in a nucleophilic addition reaction. Now what happens is, if we have a nucleophile, the nucleophile attacks the electrophilic carbon, and as a result it will split the double bond and make it a single bond. It will cleave it and make it a single bond. So let's look at what happened. We have our R1 and our R2, which is bonded to carbon and doubly bonded to oxygen. So what usually happens is we have our nucleophile, and always remember that the nucleophile has electrons. It is negatively charged. It has electrons. And so we have our carbon, we have our R group, and then we have another R group pointing away. And what happens is this carbon, we say, is doubly bonded to oxygen. So we have a nucleophile which has a negative charge on it. It will come and attack this site. It will attack this carbon, forcing one of the double bond, which is a pi bond, to break, and as such it will give its electron to the oxygen. Remember, initially the oxygen has two lone pairs on it, and so if we have one of these bond breaking, it's going to add two electrons, which means another lone pair of electron. And so what the result will be is this. We're going to have by the way, we can clean this electron for now, get these two off, and the result is an alkyl side. So we have a R attaching to this carbon, R, and then remember we now have a nucleophile, and the result is an alkoxide, which means one of these double bonds, one of these bonds will break and then give us three lone pairs of electrons on this oxygen. So this is an alkoxide. Alright, so what will happen is, the next thing that will happen is that we're going to have a proton, maybe from an acid. So let's put here a proton attached to a nucleophile, and this oxygen, which is negatively charged, will now come and pick this proton and leaving the pair of electrons on the nucleophile, and it's going to give us our final product. We had a carbon, we have our R there, and a second arrow, and then we now have a nucleophile attached to the carbon, which is going to be bonded to oxygen, which is now having a hydrogen and 2 lone pairs of electron. Remember our nucleophile with its lone pair of electron. Alright, now this is very important when we're talking about reactions of aldehydes and ketone, because you're going to meet it in a lot of reactions involving these carbonyl groups. And there are a lot of nucleophiles. We have a lot of nucleophiles, we have lots of basic nucleophiles, and we can look at some of them. We have these Grignard reagents, magnesium with any halogen, usually bromine. We have alkyl lithium. There are others like lithium aluminum hydride. We also have sodium borohydride, NaBH4. And there are also some basic ones like cyanide ion, that's Cn minus. We have some factors that affect this nucleophilic addition reaction, and the first one there is electronic effect of substituent. Now, what is this electronic effect of substituent? If we look at the carbonyl compound, we have a carbon here doubly bonded with oxygen. We have R1 and R2. Okay, what happens is if you take something like methyl, or alkyl group, they are weakly electron donating. What it means is that for the carbon, the central carbon here, there's going to be an electron donation from here. Remember, it is weakly from these two alkyl groups towards this carbon, which means it is going to nullify the partial positive charge we have on the carbon, which is going to make it to be less reactive. But if you take, let's say this is ketone. If this is ketone, and then we have an aldehyde, and hydrogen. Now, because the hydrogen is not an alkyl group and it's not electron donating, what it means is that we are going to have the partial electron donation from only one side, which is from this R1, and we are not going to have that from this H, and so it is not going to affect the carbonyl carbon, which is at the center here. Remember, it is partially positive, and the oxygen is partially negative. So because we have this electron donating effect from only one of the alkyl group, which we have on the aldehyde, it is going to make it to still be reactive as compared to the ketone. So let's put that here. Let's put aldehyde. And so this actually affects the trend in which reactivity of these carbonyl groups are moving. So if we take something like methanol, it is going to be more reactive as compared to aldehyde itself. If we take an aldehyde, we have a carbon here doubly bonded to oxygen, and then we have one R group which is bonded to hydrogen. Because we have one R group on the aldehyde itself, it's going to be donating electron to this carbon, to the central carbon, which is going to make it to be less electrophilic. And so aldehyde will also be more reactive as compared to ketone. And ketone will be more reactive compared to other groups like let's say ester. Alright, this is how electronic effect of the substituent affects the reactivity of carbonyl compound. Now another thing there is steric effect. Steric effect deals with the size of substituent which is on the carbonyl carbon. What this factor usually does is that it will, because it is bulky, it is going to affect the way the nucleophile will approach the carbon. The way the nucleophile will approach the carbon, the more bulky the group, the more it hinders the approach of the nucleophilic species which is coming to attack the carbon. Alright, so this is the end of this video. Watch out for the next video. We're going to look at some reactions. Some reactions involved in this nucleophilic reaction of aldehydes and ketones. Don't forget to subscribe and hit the like button.